In this lesson we will discuss alternative supervised ML approaches. First, we will talk about logistic regression to predict binary variables and probabilities. We will then see neural networks, decision trees and random forests. Bayesian decision trees supports vector machines and splines. In the case that the output variable of a model on which to make predictions is either a binary variable or a probability between 0 and 1, the classical linear regression is not suitable because it does bound the predicted value of the output variable, which can range from -infinite to +infinite. Therefore, in these cases, the binary variable or the probability is not considered directly as output of the model, but though a suitable monotonic transformation. More specifically, the logit function is used, which is defined as the natural logarithm of the ratio between p and 1 minus p, where p is the output variable. Thus, the linear combination of the inputs provides a value that is unbounded, but the logit function monotonically converts it onto values of p between 0 and 1. As anticipated in the previous lesson, linear regressions are the basis of more complex structures, for example, the neural networks. Here we see the basic idea of neural networks. The output is not directly described by the inputs, but some intermediate hidden layers are included. They are the so-called neurons and perform simple analysis such as a linear regression. The idea is to work in cascade, so the output variables in the intermediate layer will be combined to be the inputs of the subsequent layer and so on. Here is an example. Input data x1 and x2 are used as inputs for the three neurons. Internally, each neuron computes a linear regression. Their outputs are modified through a nonlinear function g and combined to become the inputs of the final neuron. Network complexity can be increased by extending its size. For example, the number of intermediate hidden layers can be increased from 1 layer to 2 hidden layers, from 2 to 3 and so on. Finally, also the number of nodes in each layer can be increased. In the so-called decision trees, the prediction is based on some if conditions applied on the input data. For example, we see in the figure a tree where a first branching is decided based on the value of variable a. Subsequently, a second branching is carried out based on the value of b, and sometimes a third branching is carried out based on the value of c. These models can be used both for classification or regression problems. Different trees can be fitted based on the order in which the input variables are evaluated for branching. Since there is no criterion for preferring one over another, in the so-called random forests different trees are considered together. Here, estimates are obtained in parallel from several trees, and then combined at the end. For example, in classification problems, we can choose the result mostly obtained from the different trees. In Bayesian decision trees, the conditions that determine branching in the trees are replaced by probabilistic conditions. Therefore, it is possible to repeat the prediction several times by sampling this probabilistic condition to obtain a stochastic distribution of the prediction. In the so-called support vector machines, SVMs, the domain of the input variables is partitioned into a number of regions that equals the different outcomes of a classification problem. Each region maximizes the observations of a class and minimizes the others. Then, the prediction is based on the region in which a new observation lies. Based on the type of lines used to partition the domain, also called kernel, we may have, for example, SVM with linear kernel, with quadratic kernel, and so on. In the spline regression, to better fit data, the domain of the input variable is split into regions, and a specific function, linear or not, is fitted for each region.